What's up everybody? My name is Eric. Welcome to my channel, Eric the Tutor. Today we're going to be continuing our discussion on nucleophilic acyl addition, and specifically we're going to talk about the Kiliani Fischer synthesis. So let's go ahead and jump into it. So let's go ahead and draw our carbohydrate here, and go ahead and put an R group here. Now, what are we reacting our carbohydrate with? Well, we're going to be reacting with KCN in HCl. Now, this is an important step because it's going to take our carbonyl here and we're going to protonate our carbonyl. So that's going to be the first step. So this is going to grab a hydrogen, kick on a Cl minus. Okay, so we lose Cl minus. Let's go ahead and see what we get. Here's our OH. Here's our charged up carbonyl. Awesome. So now we can see here that our CN is going to act as a nucleophile. Our CN is going to do SN2 attack, backside attack, hit our carbon, and kick up this O minus. So let's go ahead and see what we get. Here's our R group, H, OH, OH, and R. Let's go ahead and see. New lone pair was generated up there. The O is now happy. We still have that hydrogen coming off of here. And now we have our C triple bond N that was just added there. So sp3 hybridized, we have quite a few electronegative groups nearby. One of these are going to have to go. So let's go ahead and see what we do next. So our next step, we're going to react with H2 and PD, palladium, and BaSO4. Now, the palladium is a metal, and it's going to kind of act to stabilize this whole thing. So I'll go ahead and draw here a representation of what I mean. So here's our palladium. Now, let's focus in on our N triple bond C bond here, because this H2 is going to be adding on to these two molecules right here. So let's go ahead and see. We have an N triple bond to the C, and one of these bonds is going to be breaking. Okay, and this H2 that comes by, these were bonded together, but now these H2s are going to be breaking. So we can represent it with these dots. Now this H is going to be forming a bond with the nitrogen, and this H is going to form a bond with the carbon. So that's kind of why I wanted to draw. Here's the palladium. Here's the metal stabilizing this transition. This is showing us our transition state with the bonds forming and the bonds breaking. So let's go ahead and see what we get. So if we go down here, let's go ahead and get our sugar. Here's our sugar. We hit a carbon. We still have our OH. Nothing happened here. Let's go ahead and put that OH here, put the hydrogen here. Now, something I want to point out that I didn't point out up here, right? This OH can either be on the right or it can be on the left. So I'm going to represent this with this squiggle, right? So what does that mean? If we can have an OH on the right or on the left, what kind of terminology can we use? These are going to be epimers. So we're just going to keep the squiggly for now so we don't show one versus the other, but we know that we can get both in equilibrium. Great. So then this carbon is also attached to a C triple bond N. Now it's a C double bond N. We have a hydrogen coming off. There's our other hydrogen. Let's go ahead and see what we have. So now this nitrogen was triple bonded. Now it has that lone pair up there. And all right, so let's go ahead and see what our next reaction is going to be. So now, if we react this with H3O plus floating around in solution, this nitrogen can come and grab a hydrogen and kick out a water. So here's our water. Awesome. So let's go ahead and see what we get. Here's our R, OH, OH. Here's our epimeric OH, epimeric hydrogen. Here's our carbon with the hydrogen. We still have that double bond, but now this nitrogen has two hydrogens. 2 hydrogens, and it's positively charged. We also have water floating around in synthesis. So what's this water going to do? So water is going to act as a base, and it's going to come and hit this carbon and push up a lone pair onto the nitrogen. So let's see what we get. Let's go ahead and keep this going. Here's our R group, OH and an H, OH and an H, and here's our epimeric carbon, epimeric. Here's our C with a new OH2 group. Here's our OH2 group. Hydrogen coming off, single bond in nitrogen. Still has those 2 groups, but now we have a lone pair. So let's go ahead and try to resolve this problem here with the oxygen. Oxygen has 3 bonds here and a lone pair, so it's unhappy, it's got a positive charge. This nitrogen can go ahead and take care of that problem. Perfect. Let's see what we get. Here's our OH. Here's our epimeric carbon. Carbon with the H. We now have, this is an OH. Oxygen's happy. And this nitrogen has 3 bonds. So, formal charge of a positive. Our nitrogen now is a good leaving group. We have a good leaving group. This O is going to push down a pair of electrons to form a double bond, and it's going to kick out our good leaving group. The NH3 will be just fine stabilized on its own as it's no longer part of our molecule. So let's see what we get. So here's our R group. Here is our epimeric carbon. We have a C. So this is our epimeric carbon. We have a C with a double bond. Here's our double bond O with an H. So we know our oxygen is positively charged. And off of the C, we still have this hydrogen here. Great. Carbon has 4 bonds, and we just lost NH3. And we know NH3 is now just fine on its own. It has a lone pair and 3 hydrogens, so the NH3 is floating around in solution. What do you think the NH3 can do? It can come and grab this hydrogen, push it onto the oxygen. The NH3 will become NH4 plus. And our final product is going to look like, here's our H, OH, OH, epimeric carbon, and our C, double bond OH. So we see this is an aldose, and we have 1, 2, 3, 4. In this case, we have 4. Let's say it was a 5-carbon molecule. Then we have an aldopentose. Aldopentose. You can see if this R group was our CH2OH, that we started with 1, 2, 3, 4 carbons. So we went from 4 carbons to 5 carbons. And that's characteristic of the Kiliani Fischer synthesis, where we're adding a carbon group to the long carbon chain, and we're lengthening our carbohydrate. We're lengthening our sugar by 1 carbon molecule. So this is going to be our final product. Thanks for tuning in, guys. See you next time.